So this is our lecture 5.2, the idea of energy bands. And with these two upcoming slides, we will essentially introduce to you the concept of energy bands. So basically the band structure of a solid. And we will introduce that as a generalization of the math that we have dealt earlier for a hydrogen molecule that had these two electrons. So essentially we will show a classic picture also then in the final slide that helps us to understand how we can categorize different types of solids. So essentially, what is the difference between a metal, a semiconductor, and a dielectric? So this is what we will do in this lecture, and I will just get started right away since we don't have that much to cover in here. So please recall our treatment discussion during the chapter 2 that we had regarding the bonding states and the anti-bonding states. And in this treatment that we had, we were dealing with a hydrogen molecule, if I don't remember wrongly, and the number of electrons we considered was 2. So we solved the Schrödinger equation with the assumptions we had, and then we had 2 electrons to populate these different energies, different wave functions, and then we discovered that we can either have a bonding type of a state or an anti-bonding state. And now what we have here in what follows in this chapter is that we are trying to cover a more realistic piece of a solid. So for example, like a piece of a copper, aluminum, gold, silver, whatnot, metallic piece of a solid. And for that kind of solid, how many electrons that we actually have in a system, the n becomes an extremely large number. So like even in a kind of smallest possible grain that we can pretty much see, for example, with an optical microscope, the n will be several millions or billions even quite easily. Not to mention a kind of piece of a small solid that we could see with our bare eyes, or a piece of a magnifying glass. So in real life, n is essentially extremely large number. And what that then does to this kind of formation of bonding and anti-bonding states is that we don't have any more a discrete sets of energies or states, but we rather have a quasi-continuum of states that we're dealing with. And then the electronic band structure emerge subsequently. So in essence, I'm trying to clarify that in this figure of ours. So in the first case, in the A figure, we just have n equals 2. And depending on the interatomic potential, so where we are, what is the distance between the two molecules? So sorry, between the two atoms forming the molecule, we may have either a bonding state where the energy is being minimized, and we actually have a kind of like a equilibrium position for a given interatomic distance A. And then the other electron must go into this anti-bonding state that doesn't result in a minimization of energy when a molecule is being formed. And now in the B figure and in the C figure, we are increasing the number of electrons we put into our system. And essentially what we see here is that we start having more and more states, but their character remains. So that the other states are still bonding in nature, and the other ones will be anti-bonding. And then when we have really a lot of electrons that we're dealing with in a piece of a solid, so we really approach a kind of realistic piece of a solid, then these discrete energy states will turn out to become a quasi-continuum of states. And that's what we are then calling an electronic band and a band structure. And please note here that the kind of x-axis here would be our interatomic distance. So when we are dealing with a piece of a crystalline solid, that would refer to the lattice constant. And then depending on what is the lattice constant of our solid, we would be moving into a different location in our line here. So that is good to notify, especially when we would recall the kind of group 14, the carbon group 4, and its solids. So for example, carbon, germanium, and silicon, they all have a similar chemical behavior, and they form similar kind of atomic structures. They all form in a diamond structure, but the lattice constants will be different. And subsequently, there will be differences in their band structure, so that they, for example, that is the kind of original or origin of the difference why a diamond is a dielectric solid, while the silicon and germanium are semiconductors. But more on that later, like when we are going into the treatment of semiconductors. And then, as I promised in the second slide, I will show a classic picture, and this is essentially showing us how come we can understand that there are different types of solids based on their electrical conductivity. And what follows is that it is really this band structure, this electronic band structure, that dictates the electronic properties of the solid, and subsequently it is this electronic band structure that dictates are solids, is the specific solid in question, is it a good electrical conductor, a bad electrical conductor, or something in between. So this is essentially what we will be learning and what we can then do afterwards, these upcoming lectures. So we can then understand how come some solids behave so differently compared to the others with respect to their electronic properties. And this is a classical picture I'm trying to reproduce here. That will, at least at the end of these few lectures we will be having next, that what is the difference between, for example, a metal with semiconductors and a dielectric. And essentially it is the fact that in a metal, the Fermi energy or Fermi level, it seems to be smeared out here. Please note the kind of blurring of color or the gradient here, that they were speaking of finite temperatures here. In metal, the Fermi level resides somewhere in middle of a band, so that there is a kind of a continuous shift in allowed energy states. Semimetals, I won't be speaking them here. And then when we have semiconductors, there will be a band gap between the valence band and the conduction band. And this band gap will make it harder for electrons to be excited into the conduction band where they can conduct electricity. And in different types of semiconductors, like we can change slightly where we are with the bands with respect to the Fermi level, but more of that on the upcoming section on 6, focusing really on semiconductors. And then this is maybe the easiest to kind of understand now in this level of treatment that we have already introduced, is a dielectric material where we are really having a large band gap. And then all the electrons essentially are here in the valence band, and there are no electrons in the conduction band where they could actually move around in a piece of a solid and then provide a mechanism for electrical conductivity. So there's a difference between a dielectric and a metal by the fact that we actually have a band gap, an energy band gap in our dielectric that forbids electrons here to move into a conduction band, so that a large addition of energy would need to be introduced into that electron so that the electron could go all the way from the valence band to the conduction band. And here in a piece of a metal, not that much of energy increase will be needed, and these electrons can actually move in this conduction band already. So this is the difference, and in what follows we will start understanding that how we can actually how we can understand this model and how we can really understand what this picture means to us and why it's a classical picture. So this is what I wanted to say to you in the beginning of our treatment. Not sure if you fully yet understand this picture, but please we come to that later, this picture, when we can properly understand it. But I wanted to spoil to you that this is the kind of main motivation that we have in this lecture. We want to understand the electronic properties, and we want to be able to, for example, understand what makes a metal and what makes a dielectric a dielectric. So I thank you, and please hurry with me to the next lecture where we will start our treatment on the free electron model. So thanks and bye-bye.